Two dawns, one Earth. The double sun thought experiment. What if you woke up one morning and the sky had changed forever? You open your eyes to a blood-red glow leaking through the curtains. In the east, the sun is rising, but it is deeper, darker, almost rust-colored, painting the clouds in crimson. You turn to the west, expecting the usual fading night. Instead, a second whiter sun is climbing over the horizon, sharp and brilliant, cutting through the red with icy light. Two dawns, two suns. One Earth. Shadows split and overlap on your bedroom floor, one long, soft shadow stretching east, another, shorter and harsher, pointing the other way. The sky is a gradient of colors we do not even have names for yet, and within a few minutes, the entire world is lit from both sides. There is no gentle transition from night to day. The darkness is simply squeezed out. So what exactly has happened? Imagine that our familiar solar system has been rewritten. The single steady star we evolved under has been replaced by a binary pair, two suns locked in a shared orbit, with Earth circling around them both. Not in a distant sci-fi galaxy, but right here. The question is simple to ask, but far harder to answer. Would this make our world more habitable, or quietly destroy it? We often talk about the Goldilocks zone as if it is a neat ring around one calm star, a place where a planet like Earth can host liquid water, a stable atmosphere, and, perhaps life. After all, life arose here. So we treat our situation as normal. But while that feels comforting, the universe is under no obligation to match our expectations. It should be noted that roughly half of all sun-like stars are not alone at all. They live in binary or multiple systems, with two or more stars bound together. This means our single, quiet sun may actually be the exception, not the rule. So if we define habitable using only our one-star experience, how much are we missing? In the hunt for alien life, astronomers have already found real Tatooine-like worlds, planets that orbit two stars at once. Kepler revealed systems like Kepler 16b. TESS has added more, and now J-West is beginning to probe the atmospheres of planets in complex systems, forcing us to ask whether life might thrive under double sunsets and triple shadows. So, let's begin with a more personal question. In a double sun system, what happens to your actual life? Your days and nights, your sleep, your seasons, your weather, even your biology. Do you ever see true darkness? Do summers become brutal or strangely mild? Optimistically speaking, could Earth adapt, or would our atmosphere, our oceans, and our bodies be pushed past their limits? So it's time to find out the truth. In the next steps, we will walk through how two suns would reshape Earth's orbit, climate, and habitability, and what it would really feel like to stand under a sky that never quite looks the same twice. Why two suns change everything. Stakes for climate, life, and survival. So if we add a second sun, what actually changes? Everything. Adding another star is not just turning up a cosmic dimmer switch. It should be noted that a second sun rewrites the invisible scaffolding that holds our world together. Gravity changes. Earth's orbit stops being a neat, almost circular path and becomes a problem in celestial chaos. Seasons can stretch, shrink, or even disappear as the total light from the system rises and falls. The very edges of the Goldilocks zone move, breathing in and out over time. This means climate is suddenly playing on hard mode. Two stars can easily push a planet into a runaway greenhouse, like Venus, but with a more erratic thermostat if the combined brightness stays too high for too long. But while we might imagine only overheating, there is a darker flip side. If the star's separation or brightness shifts, Earth could spend long intervals with less total energy, plunging into deep, persistent ice ages. In some binary configurations, the energy input actually oscillates, so the world cycles between frozen and scorched over tens of thousands of years. Stable, human-friendly climates become the exception, not the rule. And climate is only half the story. Life on Earth evolved under one steady solar spectrum, one main color of starlight, and a reliable day-night rhythm. In the hunt for alien life, we often assume that any Earth-like planet with liquid water is enough. But what happens when you have two different stellar spectra beating down on the same atmosphere? One star might be redder, the other bluer and harsher in ultraviolet. Photosynthesis may have to split strategies, with plants or microbes tuned to different colors at different times of the day. Circadian clocks, from human sleep cycles to plankton migrations, could be constantly forced to reset as the pattern of bright, dim, and never quite dark keeps shifting. Optimistically speaking, evolution is inventive. Life might adapt to double dawns and triple shadows, yet even small changes in the stars themselves can be catastrophic. A slightly more massive companion can pull Earth's orbit into elongated loops. A tighter binary can spin the stars up, boosting flares and high-energy radiation that strip atmospheres and erode habitability. Modeling a two-sun Earth means combining orbital mechanics, stellar physics, atmospheric chemistry, and biology, and the parameter space is brutal. Tiny tweaks can flip the outcome from barely changed to instantly doomed. So, let's begin to narrow this down. Instead of every wild possibility, we will test a few concrete, realistic arrangements. A distant solar companion that barely tugs on us, a close binary pair that Earth orbits from afar, and a true circumbinary orbit, a Tatooine-style path around both stars at once. Which of these, if any, could keep our planet stable, habitable, and recognizable as home under two suns? So it's time to find out the truth, and the first scenario is much closer to reality than you might think. From sci-fi to sky-fi, real planets with two suns, we just imagined 3 ways to give Earth a second sun. But, is any of this more than a cinematic fantasy? In the hunt for alien life, this is where things become very real, very quickly, because telescopes have already found planets with two suns. Not in a movie, not in concept art, but in hard, carefully checked data. These are called circumbinary planets, worlds that orbit around a pair of stars at once. For a long time, astronomers suspected that such orbits would be too chaotic, that gravity from two stars would fling planets out of the system. But, while that sounded reasonable, it turns out the universe did not get the memo. Enter Kepler-16b. This was the first unambiguous, Tatooine-like planet we detected, and it changed the conversation. Kepler-16 is a binary system about 200 light-years away, with one star slightly smaller and cooler than the Sun, and a second, dimmer red dwarf companion. The two stars orbit each other closely, completing a dance in just over 41 days. Kepler-16b circles both of them in a nearly perfect stable orbit lasting about 229 days. So, let's begin with what that means. From the surface of Kepler-16b, if it had a solid surface, you would watch two suns rise and set together, sometimes one eclipsing the other, casting double shadows that stretch and twist. The planet itself is cold and Saturn-like, not Earth-like or habitable as we know it, but its very existence shattered the old assumption that binary stars are planetary no-go zones. This means that a double-sun Earth is not forbidden by physics, it is just one version of a pattern the cosmos already uses, and Kepler-16b was only the opening act. The Kepler-47 system pushed things further, revealing not one, but multiple circumbinary planets around a pair of sun-like stars. One of those worlds, Kepler-47c, orbits right in the combined Goldilocks zone, where temperatures could in principle allow liquid water. Suddenly, we had a template, a multi-planet system, 2 central suns, and at least one orbit with roughly the right amount of starlight for life. Pattern interrupt. For a moment, forget Earth. Imagine standing on that habitable zone planet, watching 2 stars trace complex paths through the sky over the course of a year. Daylight would subtly pulse as the stars moved closer together and farther apart in your sky. Seasons could be driven not just by tilt, but by the changing geometry of the binary itself. It should be noted that Kepler-47 is not unique. We now know several circumbinary systems, and roughly half of all sun-like stars in our galaxy live in binary or multiple systems. Optimistically speaking, our single, quiet sun might be the exception, not the rule. So it's time to find out the truth by studying these real two-sun systems with Kepler, TESS, and now, Jubble West. We can reverse engineer what would happen if we dropped Earth into a similar orbit. In the next section, we will take those templates and stress test our own planet under double starlight, our new cosmic microscope, how telescopes probe double suns. So if the universe is full of double suns, how do we actually interrogate them? How do we move from pretty sci-fi artwork to hard numbers about whether a planet in such a system could stay habitable? In the hunt for alien life, our first big breakthrough was Kepler. This space telescope simply stared at over 100,000 stars at once, measuring their brightness with absurd precision. Whenever a planet crossed in front of its star, Kepler saw a tiny, regular dip in light. One dip is a hint. A whole pattern of dips with the same depth and timing is a planet. But while that sounds straightforward around a single star, what about a binary? Surprisingly, the same method works. In a close double star system, the stars already eclipse each other, so the light curve is full of repeating wiggles. When a planet transits as well, it adds extra smaller dips on top of that pattern. This means we can pick out a circumbinary planet like Kepler-16b, which orbits both stars, from the way those extra shadows stars appear and shift over time. It should be noted that the real power comes from timing, by tracking exactly when each transit happens and how deep each one is. Astronomers can reconstruct the entire geometry of the system. Is the planet tightly bound to just one star, tracing a small, nearly circular orbit, or is it looping around both suns at once, with the stars dancing in the middle? The details of those dips tell us where the Goldilocks zone really lies and how stable it might be over millions of years. Then we add the James Webb Space Telescope. JWST does not just count dips in brightness, it dissects the light itself. When a planet passes in front of its stars, some starlight filters through the atmosphere of that world. In infrared wavelengths, Webb's huge mirror can split that light into a spectrum, revealing molecules, clouds, and even how heat is being moved around the planet. So, let's begin to see two sun worlds not as blurry dots, but as physical climates. Even in complex multi-star systems, this spectral fingerprint lets us test whether atmospheres are being stripped away by extra radiation, or whether a planet maintains a comfortable heat balance. Optimistically speaking, a JWST can tell us if a double sun setup is more like a gentle cosmic heat lamp, or a slow atmospheric blowtorch. So it's time to find out the truth. Together, Kepler, TESS, and JWST act like cosmic truth machines, turning our speculation about two sun Earths into testable physics and climate models. And by the end of this video, we will not just ask whether Earth could survive with two suns, we will be able to point to specific orbital arrangements and say, this kind of double star might make our planet more welcoming to life, and this kind might quietly destroy it. Safe haven or slow roast? The double sun dilemma. So what does a second sun really mean for us? Is Earth upgraded into a gently lit oasis with fewer extremes, or placed on a slow, precise path to being roasted and stripped bare? This is the core tension in a double sun universe. The same physics that can smooth out a planet's climate can also tear its orbit apart and sandblast its atmosphere. So it's time to find out the truth. In a two-sun system, are we talking about a safer, more habitable Earth, or a beautifully lit death trap? Imagine the first optimistic case. Far out beyond Pluto, the Sun has a wide, distant companion star, maybe a small orange star that takes thousands of years to complete one orbit. From Earth, it never blazes like our Sun, it glows as a permanent, bright evening star, just enough to soften our nights and stretch twilight. Its gravity tugs on the whole system very gently, helping to keep comet reservoirs and planetary orbits more orderly instead of chaotic. In this version, day-to-day life barely changes. You could still sleep under mostly dark skies, still grow crops under one main star. But the second sun adds a subtle, stabilizing hand. Optimistically speaking, long-term climate swings might be reduced, with fewer wild excursions that freeze or fry the planet. In the hunt for alien life, this kind of quiet binary could actually expand the Goldilocks zone and keep Earth-like worlds temperate for longer. Now, flip the configuration. Instead of a remote companion, picture a close, equal-mass partner, a true double star only a few tens of millions of kilometers apart. Earth orbits both of them together, like the circumbinary planets Kepler has already discovered. When the two suns line up, total light surges. When they separate, the planet receives a flickering pattern of heating and cooling. Seasons stop being simple. They become a complex interference pattern of orbits and alignments. This means more energy, more ultraviolet radiation, and potentially far more stellar activity. Close binaries can spin each other up, driving stronger magnetic fields and violent flares that chew away at a planet's atmosphere. You might see triple shadows at noon, and a sky that never quite gets dark, but you also live under a constant threat that one bad stellar storm could sterilize continents. It should be noted that both of these futures are written in the same equations. The difference between pleasantly lit oasis and slow roast is not magic, it is orbital distance, stellar mass, and how the total light varies with time. So the sharper question is not just, could Earth orbit two suns? It is, could you live there? Could you sleep, grow food, build a civilization, and trust that the climate will still support your grandchildren? So, let's begin to answer that by walking through three concrete possibilities: a distant twin, a tight binary, and a true circumbinary orbit. One of them leads to a surprisingly livable, if very alien, Earth, but not the one you might expect. Welcome to the channel, our roadmap through a two-sun Earth. So if one of these three double-sun setups could actually work, how do we figure out which one? And how do we move beyond a cool movie shot and into real physics? I am, and this is, where we take big, cinematic what-if scenarios and tie them down with the best astrophysics and planetary science we have. In the hunt for alien life, we usually look outward to some distant Earth-like planet in a strange system. Today, We are turning that lens inward and asking how our own world would behave under two stars. To do that properly, we need a roadmap. First, we will build a basic toolkit. What kinds of double star systems actually exist out there? Wide binaries that barely notice each other, tight, whirling pairs, true circumbinary systems, like Kepler-16, where a planet orbits both suns at once. We will look at how their gravity works, how their orbits dance, and what that does to a potential Goldilocks zone. Then, we will take Earth on a tour through three main configurations. We will place a distant twin sun far beyond Pluto and watch how little and how much that really changes. We will drop a bright companion close in, forcing our planet to orbit just one member of a tight binary. Finally, we will move Earth outside both stars into a shared circumbinary orbit and ask whether that could ever feel stable. But while that tour sounds simple, the physics underneath is not, so it's time to find out the truth in a systematic way. For each setup, we will start with gravitational stability and orbital mechanics. Does Earth's path stay predictable, or does it slowly unravel over millions of years? This means checking resonances, long-term wobbles, and whether seasons stay on any kind of schedule. Once an orbit survives, we will layer on climate and seasons. How hot does the surface get when both suns line up? How deep does winter bite when they separate? Then we will climb one level higher to radiation and atmosphere. It should be noted that many multi-star systems are more active than our sun, so we will ask whether flares and ultraviolet light strip the air or leave it mostly intact. Only then do we talk about life. We will explore biology and human experience under dual light, plants adapting to two-color temperatures, circadian rhythms trying to track a sky that never quite repeats, and what night means when one star sets as the other rises. Optimistically speaking, some of these worlds might still be habitable, just very different. Here is the pattern interrupt. As we move Earth through each scenario, do not just picture a globe on a diagram, picture your town, your horizon, your calendar. Where would the second sunrise appear? How long would shadows stretch? By the end of this episode, you should be able to look at almost any double star system we discover, from Alpha Centauri to a new Kepler binary, and make an educated guess about what an Earth-like world there would actually feel like. So, let's begin with the stars themselves. Binary Star 101. How two suns dance and drag their planets. If we want to put a second sun in our sky, we first have to ask a deceptively simple question. How do two stars dance together in the first place? Because the way they move decides whether a planet like Earth survives or gets flung into the cold of deep space. In the hunt for alien life, astronomers have learned that double stars are not rare curiosities. Roughly half of sun-like stars live in binary systems. But while that sounds chaotic, their orbits actually fall into a few main patterns that we can understand. This means we can start to predict which setups are friendly to an Earth-like world and which are instant cosmic eviction notices. At one extreme, we have wide binaries. Picture two suns so far apart that each one behaves almost like a separate miniature solar system. A planet can comfortably orbit one star in what we call an S-type orbit, while the other star just drifts in the background, tugging gently over tens of thousands of years. Alpha Centauri A and B are close to this regime. For a world like Earth, this is the least dramatic way to get two suns, one main star, one distant companion. At the other extreme, we have tight, close binaries. Here the stars race around a common center, often in just days. Planets cannot safely cling to one star alone. The gravity is too chaotic. Instead, they must orbit both stars together on a wide loop. That is a p-type, or circumbinary orbit, like the famous Kepler-16b, the first confirmed planet with two suns in its sky. Between these two extremes lies the danger zone. Intermediate separations often produce unstable orbits where a planet is pulled first one way, then the other, until it either crashes into a star or is ejected entirely. It should be noted that nature still tries to put planets there, but most do not last for billions of years. So what actually controls where a stable orbit can exist? Two main ingredients: the masses of the stars and the distance between them. Heavier stars pull harder, carving out larger regions of chaos around themselves. Wider separations open up safe S-type zones around each star. Closer separations can create a single stable circumbinary zone farther out. Optimistically speaking, there is usually at least one ring of stability, but its shape is rarely a simple circle. And the habitable Goldilocks zone? In a binary, it can warp, overlap, and even breathe in and out as the stars move. When the stars are on the same side of their orbit, a planet may be briefly overheated. When they are opposite, light levels drop. Over long cycles, climates can swing in ways our single sun Earth never experiences. So it's time to find out the truth for our own world. In the rest of this episode, we will test 3 specific scenarios: Earth with a distant sun, like companion, Earth in a tight, equal mass solar binary on a circumbinary orbit, and finally, Earth circling a mismatched pair, our sun and a dim red dwarf. How different would our sky, our seasons, and our chances for life really be? Our sun doubled, profiles of the stars in a 2-sun sky, so if we double the number of suns, what exactly are we doubling? To answer that, we have to look closely at the stars themselves, because the type of second sun we add will decide whether Earth stays habitable or slowly turns hostile. Our current sun is a G-type star, a middle-of-theroid yellow-white star in the grand census of the universe. It outputs a broad spectrum of light, peaking in the visible, with enough ultraviolet to drive chemistry, but not so much that it constantly shreds our atmosphere. It should be noted that our sun is relatively calm for its class, its magnetic cycles are mild, its flares modest, and that long-term stability has given Earth a remarkably steady climate over billions of years. Our entire biosphere has evolved under that quiet, predictable glow. So, let's begin with the simplest upgrade, a near twin. Imagine a second G-type star, almost the same mass and luminosity as the sun, locked with it in a tight binary, and Earth on a wide circumbinary orbit around both. When the 2 stars share the sky, their combined brightness would be roughly double what we receive now. Midday would be almost painfully intense, shadows razor-sharp, and the Goldilocks zone around the pair would shift outward to keep a planet like ours from overheating. But while the total light might be balanced by a slightly larger orbit, the pattern of that light over time would change dramatically. When one star dips behind the other, or sets earlier, the flux would dip and rise in complex cycles. This means seasons within seasons, long subtle beats of warming and cooling layered on top of Earth's usual yearly rhythm. In the hunt for alien life, such nested cycles could be a challenge, but also an engine for evolution. Now contrast that with a very different companion, a red dwarf. Smaller, cooler, and far dimmer than the sun, a typical red dwarf might contribute only a fraction of the total visible light, but it would pour out proportionally more red and infrared radiation. The sky under such a pair would be extraordinary. A white-yellow primary casting familiar bluish daylight, and a deeper, embered secondary that tints the landscape when it dominates. Shadows could split into 2 colors, sunsets might layer crimson on top of gold, but while a red dwarf looks gentle, it often behaves anything but. These stars tend to have intense magnetic fields and frequent flares. Compared to their size, they can unleash huge bursts of ultraviolet and X-ray radiation. In a close binary, tidal forces between the stars can spin them up, amplifying that activity. So it's time to find out the truth about multiple stars. In tight systems, their mutual gravity can keep their interiors stirred and their surfaces angry for billions of years. This means more flares, more high-energy particles, and a greater risk that a planet's atmosphere is gradually stripped or chemically altered. Optimistically speaking, a 2-sun Earth could still be habitable, but the details of the spectrum matter. Different colors of starlight would favor different pigments for photosynthesis, reshape how much energy reaches the surface, and change how life tracks day and night. In the next section, we will take those stellar personalities and see how they rewrite Earth's sky, climate, and daily experience. When 2 suns behave, the surprisingly gentle wide binary Earth, so if different stellar colors can rewrite biology, what happens when we barely change the script at all? What if Earth kept our familiar sun, but added a second, well-behaved partner, far out in the dark? So, let's begin with the calmest version of a 2-sun universe. In this wide-binary setup, our sun remains the main star. Earth still orbits at 1 astronomical unit in the usual Goldilocks zone, but far beyond Neptune, tens to hundreds of astronomical units away, a second sun-like star loops around both of us. On the sky, it would not blaze overhead like a twin noon. Most of the time, it would look like an unusually bright star, or at best a tiny distant sun hovering near the horizon. This means the second star's gravity is important, but not catastrophic. At separations of say 100 AU, it tugs on the entire system gently, rather than yanking Earth out of orbit. Orbital mechanics tells us that as long as Earth stays tightly bound to our primary star, and the companion stays far away, Earth's year remains almost exactly 365 days. No wild slingshots, no planet-flinging chaos. Instead, the companion slowly reshapes the outer architecture, the Oort cloud gets stretched, comet orbits are tilted, and over millions of years, the eccentricities of the planets drift in slow, graceful cycles. what about the light in our sky? At 100 AU, a sun-like companion would deliver only about 1/10,000th of the brightness we receive from our own star. It should be noted that that is far less than a full moon, but still bright enough to cast the faintest of shadows under pristine dark skies. Nights would rarely be perfectly black. Occasionally, geometry would line up so that as our sun was setting, the distant companion was just rising, giving the impression of a delayed, ghostly second sunrise, or a pale twin sunset on the opposite horizon. Beautiful, yes, blinding no. So would Earth's climate care? In the hunt for alien life, we often imagine dramatic temperature swings in multi-star systems, but here the extra energy is negligible. Average global temperature stays essentially Earth-like. Seasons remain driven by our axial tilt, not by the distant partner. The real changes unfold on timescales longer than human history. As the companion star crawls along its huge orbit over tens of thousands of years, its gravity very slightly shifts Earth's eccentricity and inclination. That could modulate ice ages and long-period climate cycles, but far more subtly than the wild scenarios we sometimes fear. Optimistically speaking, this is the safest two-sun configuration for a habitable Earth. Daily life would feel almost normal, yet that safety comes with a twist. The sky is only modestly different. So it's time to find out the truth about the more extreme option, where the second sun moves in close, and the sky never looks the same 2 days in a row. Into the maelstrom, Earth in a tight, equal-mass solar binary. So what happens if we take that safe, wide binary and crank the chaos dial up? What if Earth orbits not one calm sun plus a distant partner, but a tight pair of equal stars locked in a fast gravitational dance? So, let's begin with the layout of this extreme system. Picture two sun-like stars, each about our sun's mass, circling each other at a distance comparable to Mercury's orbit or even smaller. They whirl around a shared center of mass every few weeks or months. Earth, instead of orbiting one star, follows a wider circumbinary path that wraps around both, staying several times farther out than the stars are from each other. From the ground, the sky would feel restless. Some days, both suns would rise almost together, blazing side by side and casting twin razor-sharp shadows. On other days, one star would lead and the other lag. So morning might begin with a single brilliant disk, and only later would a second fainter sun climb into view. There would be afternoons with double shadows slowly twisting around you, and evenings where one sun sets while the other still hangs high, stretching daylight into something that barely counts as night. And sometimes, the choreography becomes stunning. Because the stars orbit each other, there will be rare alignments where one passes directly in front of the other. One midday, the brighter sun might suddenly dim as its twin eclipses it, turning a blazing sky into a strange, ringed halo for an hour. It should be noted that in a universe full of predictable sunrises, this would feel almost supernatural. But can Earth's orbit in such a system actually be stable? The physics says yes, if we stay far enough out. As long as our orbit radius is several times larger than the separation of the two stars, the combined gravity acts, on average, like a single, slightly wobbling star. This means Earth could remain on a nearly circular path for billions of years. Move us closer in, though, and the gravitational tug-of-war starts to pump up our orbital eccentricity, turning our nearly circular orbit into a stretched ellipse. Over time, that can drift into chaotic territory, with climate swings far beyond anything in our current geological record. Those swings start with the light itself. When both stars are on the same side of their orbit, Earth sees them clustered together in the sky, and the total energy we receive spikes. Weeks or months later, when the stars are on opposite sides, their light spreads out, and the combined flux dips. Layer that on top of our normal axial seasons, and we get long, subtle binary seasons where summers are sometimes supercharged, and sometimes strangely muted. In the hunt for alien life, that kind of slow, rhythmic forcing could drive powerful ice ages, megastorm belts, or even periodic global thaws. Our atmosphere would have to buffer not just daily weather, but these deep, binary beats. There is another complication. Tight binaries are usually not quiet. Tidal forces between the stars can spin them up, stirring their magnetic fields and driving more flares, more ultraviolet, and more charged particle storms. Over hundreds of millions of years, that extra aggression can erode an atmosphere, strip ozone, and hammer the surface with radiation. Optimistically speaking, a strong magnetic field and thick air might still keep the surface habitable, but the margin for error shrinks. So it's time to find out the truth about an even stranger possibility. What if those two suns are not twins at all, but a mismatched pair, one hot and blue, one small and red, pulling Earth between two very different kinds of starlight? Mismatched suns, sun plus red dwarf, and the warped habitable zone. But what if that mismatched pair is even stranger than we first imagined? Instead of two hot blue-white suns, picture our familiar yellow sun, locked in a tight dance with a small, cool red dwarf, and Earth orbiting both from afar. This is a mixed binary. binary, one star like home, one more like TRAPPIST-1, but closer and brighter in our sky. The two stars whirl around each other in a compact orbit, maybe every few weeks, while Earth traces a wide circumbinary path around their combined center of mass. From the ground, the sun would dominate, but the red dwarf would still be a constant, ruddy presence, sometimes close to the sun, sometimes pulled away across the sky. In the hunt for alien life, we often talk about a neat Goldilocks zone, a simple ring around a single star. Here, that idea breaks. The habitable zone is no longer a clean circle. It is a breathing, oscillating shell of warmth. As the sun and the red dwarf move closer together or farther apart in their orbit, the total light at Earth's distance rises and falls. Some months, the two stars line up, their energy adding to push Earth toward the inner edge of the habitable band. At other times, they are spread out, and the combined light drops, nudging Earth back toward the outer edge. This means climate is not just about seasons from axial tilt, but about stellar choreography. Long-term weather patterns could follow the binary's period, subtle cycles of extra heating and gentle cooling layered on top of normal seasons. Optimistically speaking, oceans and a thick atmosphere might smooth out those swings, but while the climate might average to Earth-like, the radiation environment would not. It should be noted that red dwarfs, even small ones, can be fierce. Relative to their size, they produce more flares and high-energy particles than a sun-like star. Our sun in this system offers steady, familiar light, but the red dwarf adds sudden, violent space weather. When a major flare erupts, streams of charged particles would slam into Earth's magnetic field more often than we experience today, compressing it, shaking it, and occasionally punching through near the poles. Over millions of years, that extra punishment matters. Repeated flares and stronger stellar winds could gradually erode the upper atmosphere, stripping away lighter gases and thinning any protective ozone layer. A planet here would need a powerful magnetic field and a dense atmosphere just to hold the line. Without them, ultraviolet and particle radiation could reach the surface in doses that challenge complex life. So it's time to find out the truth about habitability in such a system. Does the added red and infrared light, plus occasional energy spikes, create a richer, more resilient biosphere, with life adapted to dual colors and variable skies? Or does it slowly sterilize exposed land, forcing life to retreat underground or deep underwater, where rock and water can do what the atmosphere no longer can? And if Earth could survive that, what happens when the binary itself starts to change? Triple shadows and endless twilight, daily life under two suns. So if the stars themselves are changing, what does that actually feel like on the surface, on an Earth-like planet that now orbits two suns? Because for us, the first thing we would notice is not the extra radiation, it's the sky. Sunrise stops being a single clean moment. On some days, the dimmer, redder companion star would slip above the horizon first, painting everything in a coppery half-light. Street lamps would click off, birds would start to sing, our brains would say morning, yet the landscape would still look strangely muted. Then, minutes or even an hour later, the primary star would rise, and we would experience a second, sharper sunrise as colors suddenly snap into full brightness. But on other days of the binary orbit, timing lines up. Both suns crest the horizon together, their light stacking into a blinding double dawn that throws harsh contrast across every surface. Do we set our alarm for the first sunrise, the second, or the days when both arrive at once? This means even the simple act of waking up with the sun becomes a choice, not a default. And what about night? In the hunt for alien life, we often picture a quiet, dark sky as a universal backdrop. Here, true darkness almost disappears. In many stable circumbinary configurations, at least one star sits above, or just below, the horizon most of the time. Even when both have technically set, scattered light in the upper atmosphere would keep the ground in a deep, bluish twilight. The Milky Way becomes something rare and ceremonial, visible only during brief windows when both suns slip far enough below the horizon and the moon stays out of the way. It should be noted that shadows stop behaving the way we expect, too, at noon. A tree might cast two crisp, diverging shadows, one pale, one warmer and red-tinted. As the stars move in their dance, those outlines slide, cross, and briefly merge into a single dark band before peeling apart again. Add moonlight reflected from one side of the binary, and suddenly, there is a faint third shadow. Offset and ghost-like. Just walking down a city street would feel subtly uncanny as your own silhouette stretches in multiple directions at once. Timekeeping has to evolve. A simple 24-hour day, tied to a single rising and setting, no longer tells the whole story. Civilizations here would track a longer binary cycle, the period of the star's mutual orbit, because that slow rhythm controls when the suns align, when their light adds, and when it partially cancels. Optimistically speaking, those rare, perfectly balanced twilights or spectacular double eclipses might become the anchors of calendars, the basis for festivals, even the way eras are named. But biology cannot wait for festivals. Our circadian rhythms rely on clear contrast between day and night. So how do humans, animals, even plants adapt when the sky refuses to go fully dark? We might evolve stronger internal clocks, less easily fooled by stray light. Cultures could mandate dark hours indoors, with shuttered windows and carefully filtered lamps, just to let brains reset. Wild species might specialize, some tuned to the dimmer red star, others to the brighter primary, and a few exploiting the perpetual twilight in between. And yet, if daily life itself becomes this complex, what happens when the binary's long-term cycles push the entire climate into an equally strange rhythm? Alien photosynthesis, how life evolves under double starlight. To answer that, we have to ask something even stranger. Under two suns, what does daylight actually mean for life? Because if the sky itself is changing on multiple overlapping cycles, then evolution is forced to redesign the basic machinery of how organisms eat light and tell time. On Earth, photosynthesis is tuned with exquisite precision to our single star. Chlorophyll absorbs mainly red and blue wavelengths, leaving green reflected, because that is where the sun's spectrum and our atmosphere deliver the most usable energy. But now, imagine our planet in a circumbinary orbit, one sun like star blazing white-yellow, and a cooler red dwarf companion bathing the world in infrared-rich light. In the hunt for alien life, this is not just a cosmetic change. This means the entire photosynthetic toolkit would be rewritten. Instead of a single dominant pigment, plants might evolve whole suites of light-harvesting molecules. Some would grab the familiar visible wavelengths from the primary star. Others would reach deeper into the infrared, tuned to the red dwarf's glow. It should be noted that we already see hints of this flexibility on Earth. Deep-sea bacteria use infrared from hydrothermal vents, and some purple and brown microbes use alternative pigments instead of chlorophyll. Now scale that up to forests. Picture hillsides of multicolored foliage, not just in autumn, but all year. During the red hours, when the dwarf star dominates and the primary dips low or slips behind it, dark, almost black leaves drink in every stray photon, maximizing absorption. Then, as double sun noon approaches and both stars blaze overhead, other plants flash silvery or pale, with reflective, waxy leaves that bounce away excess light to avoid overheating. A single tree might even carry both strategies: inner canopy leaves black and light-hungry, outer leaves bright and protective. But while leaves adapt to the spectrum, bodies must adapt to the rhythm. Our own biology runs on a roughly 24-hour circadian clock and trained to one sunrise and one sunset. On a two-sun Earth, organisms could evolve dual clocks, a fast one tied to the primary star's day-night cycle, and a slower, deeper clock synced to the binary orbit that modulates total light and climate over weeks or months. Migration, flowering, breeding, even hibernation might follow the long binary beat rather than the simple daily cycle. There is a harsher side. Red dwarfs, especially in tight systems, can flare violently, blasting ultraviolet and charged particles, so it's time to find out the truth about survival under that kind of stress. Plants might evolve thicker cuticles and sacrificial outer tissues to absorb radiation. Animals could develop more powerful DNA repair enzymes, pigment shields in skin and eyes, or behaviors that keep them underground or underwater during peak activity. If any true night still exists, nocturnality becomes a major refuge. Optimistically speaking, two suns do not forbid life, they diversify it. The combined light fields, shifting shadows, and variable radiation carve out a richer landscape of ecological niches than our single sun Earth. In such a system, we should expect explosive diversification: cliffside plants specialized only for red hours, aerial plankton surfing thermal updrafts at double sun noon, burrowing creatures timing emergence to the safest phase of the binary cycle. And if evolution can adapt leaves, clocks, and genomes to this double starlight dance, we have to ask one more question: could minds and civilizations also learn to ride these cycles, or would the sky itself be their greatest obstacle? Would we make it? Civilizations, technology, and long-term survival minds under two suns. If biology can adapt, can culture keep up, or does civilization itself become a victim of the sky? So, let's begin with the very first storytellers looking up. Two bright lights crossing, separating, and reuniting over years or decades would be impossible to ignore. We can imagine mythologies of twin creator gods, rival siblings, or cosmic lovers. Each eclipse or close approach turned into an omen. This means the sky is not just a backdrop, it is a drama, with visible, long-period cycles. Early farmers would have to track those cycles. A simple solar calendar would fail if the combined brightness and seasons drifted over multi-year beats as the stars orbit their common center. So, long before telescopes, priests and astronomers might discover that there is not one year, but several overlapping great years defined by the dance of the suns. In the hunt for alien life, we often assume our concept of a year is universal. Here, it would be obviously relative. That complexity could be a gift. Binary motion is a built-in physics lesson. Careful observers would notice that when the stars are far apart, winters sharpen or summers soften, and when they draw close, the climate shifts again. It should be noted that this is essentially orbital mechanics written across the sky. Civilizations might infer gravity's rules and even the existence of invisible orbits far earlier than we did on our single sun, Earth. But the same stars that teach could also threaten. 2 active suns mean stronger space weather, tangled magnetic fields, and more intense radiation belts. Early radio experiments might be plagued by mysterious static whenever the stars align a certain way. Telegraph lines, then power grids, then primitive satellites would all be stress-tested by storms, far harsher than our worst solar flares. Optimistically speaking, that pressure forces rapid innovation. You do not launch fragile metal boxes into orbit, you design them from day one with heavy shielding, hardened electronics, and redundant systems. Space agencies in a 2-sun system would treat radiation like we treat vacuum. A basic fact, not an edge case. So would we make it? In a habitability configuration, where our Earth-like planet orbits one star, and the companion is a distant sun in the background, the answer is almost certainly yes. Climate is only slightly perturbed. The second star is more calendar curiosity than existential threat. A tight, equal mass binary, with Earth circling both, is harder. Habitability survives only if the planet keeps a strong magnetic field and thick atmosphere to blunt flares and high-energy particles. Civilizations here might cluster under auroral belts, build underground data vaults, and schedule launches in the quiet phases of the binary cycle. The most extreme case is a mixed pair, a sun-like star plus a close red dwarf. Here, the red dwarf's flares and the sun's long-term brightening fight over the atmosphere. Worlds could still be habitable, but only with aggressive adaptation, global radiation shelters, high-latitude cities, and perhaps engineered magnetospheres. Over deep time, the story changes again. Binary stars exchange angular momentum. Orbits can widen or shrink. The sun-like star swells and dies in a few billion years, while its red dwarf partner burns almost unchanged for trillions. Picture a very ancient Earth. If it survives orbital reshuffling, circling a faint red ember, its once brilliant primary, long gone. So it's time to find out the truth about perspective. If minds evolve under 2 suns, with layered days, braided years, and a sky that never quite repeats, would our single sun physics and tidy calendar feel incomplete to them? Would day and year even be meaningful words, or just local customs from a strangely simple corner of the universe? And if that is the case, what else about our definition of a habitable world might be far more parochial than we think? One quiet sun, recap, cosmic perspective, and your 2-star choice. If our version of habitable is just one local custom, what have we really learned from this 2-sun thought experiment? We have, in a sense, tested how fragile our normal actually is. We began with the gentlest option, a distant companion star, a wide binary where a faint second sun crawls slowly across the sky over decades. In that case, Earth's orbit hardly changes, seasons stay familiar, and life mostly shrugs. The drama is in the long-term tides, in slow climate nudges, in subtle shifts that only precise data and patient civilizations would notice. This means that even in a multi-star system, a planet can still feel very Earth-like on the surface. Then we pushed harder into a tight, equal mass binary. 2 bright suns, dancing around each other quickly, pouring out light and magnetic storms. The Goldilocks zone becomes a moving target. Days fracture into complex patterns of double dawns and overlapping shadows. Space weather turns risky, flares and winds threaten to strip atmospheres unless a planet is shielded. Yet, optimistically speaking, stable orbits are possible. Just as Kepler 16b has shown us, a world there could still be habitable, but its sky would never let you forget the complexity of its system. Finally, we mixed our familiar sun with a small red dwarf companion. Here, the habitable zone warps and stretches. Some orbits are bathed in steady yellow light with a faint red ember. Others endure long cycles of deep cold and sudden warmth as the 2 stars trade places in the sky. Photosynthesis might split into 2 strategies, plants tuned to white sunlight and others drinking in the red dwarf's glow. In the hunt for alien life, these hybrid systems may be some of the most creative laboratories the universe has built. It should be noted that our single, relatively quiet star is not the default. Roughly half of Sun-like stars live with partners. Multi-star systems, with all their chaotic orbits and braided years, are normal, and yet, even there, we see evidence that planets can settle into long-lived stable paths with the potential for thick atmospheres, liquid water, and perhaps civilizations that consider two suns completely unremarkable. So, step outside tonight and look toward where the sun has just slipped below the horizon. Ask yourself, how different would your sense of reality be if a second star followed it down, or rose to replace it? How delicately tuned is this quiet, solitary glow that we treat as obvious? So it's time to find out the truth about your own two-star preference. If you could choose, which real stars would you put in Earth's sky? Sun plus Alpha Centauri A for a bright twin, Sun plus a dim red dwarf for subtle, eerie nights, or something more exotic entirely? Tell us in the comments, and explain why. If you want to go deeper, watch our other episodes on real circumbinary planets and on how Dwest is dissecting multi-star systems in detail. Subscribe for more What If journeys grounded in current space science, because the next twist in how we define a habitable world may already be hiding in the light of another star we have barely begun to study.